All right. Welcome everyone. So as always, what we'll do is we'll spend a couple of minutes now just waiting as people are joining the call. So as always, I'm just going to take a moment to sort of outline the structure of the session. So as we have done over the last few weeks, in the first half, we'll have the seminar being delivered by Maylee this week. And then in the second half, we'll be doing a Q&A. And each one of those will be roughly about 30 minutes. Of course, you're still welcome to ask questions while the talk is being given, and you can do that by using the Q&A function in Zoom. The thing is, we might not get to your question unless it's directly related to something on screen. So if you're clarifying a point that's been made, we'll probably pick that up, but if it's anything else, we'll probably wait until the Q&A. So as before, we are looking for questions to do with the content of the seminar. So we won't be answering questions to do with life at Cambridge and the computer science course at Cambridge. And that's just because we'll be doing sessions on this in the future. All right, so as we usually do, I'll be doing a starter poll, which you should have popping up onto your screen now. So really simple. So 2 questions. Did you attend last week's seminar? And if you did, what was one interesting thing that you learned in last week's seminar? So yeah, when you get a moment, please do fill in that starter poll. And once we've got maybe 70 or 80% of you filled that in, we'll have a look at some answers and then we'll get going. All right, so far we've had about 30% of you answer, and we've got around 80% of you attended the seminar last week, which is great. Great to see loads of people attending every single week. I also split up the question this week, so I was quite interested to see how many people have been watching the recordings. So we've got a few people, about 10% who watched the recording, and then only 5% who didn't watch the recording, didn't come watch the recording. All right, so we've had about 60% of people reply to the poll. So what we'll do is we'll wait for another maybe 20 seconds, and then we'll close the poll, and we'll have a look at some answers quickly before jumping in. All right, so yeah, 10 more seconds, and then I'll close the poll. So if you've got, if you've started an answer, do try and submit it soon. All right, so I will be closing the poll now, and we'll have a look at some of these answers. So yeah, so we've got 92% of you attended last week's seminar, 5% watched the recording, and 3% didn't watch the recording. And then we'll have a quick look now at some of your answers of what you found most interesting about last week's seminar. So someone says, I learned how routers fundamentally work, the history of networks and data packets, limitations of traditional networks, applications of different software. Lots of people enjoyed learning about the history of networks, the use of software-defined networking, making things effective and reducing latency, that software-defined networking is more flexible than traditional. Again, the history of networks, how to add security to routers, loads and loads of things there that people have learned. Great, yeah, thank you so much for sharing that in the poll. What I'm going to do now is I will hand over to our speaker for today's session.
Okay, so good afternoon, everyone. So my name is Maylee Kossé, and I will share my screen for the presentation. Just a second. Okay. So everyone can see the presentation?
Yeah, that
okay,
looks
perfect. Good. Okay, so So I'm a physicist, and currently I'm working as a postdoc at the University of Cambridge in the Department of Material Science and Metallurgy. And so today I'm very excited to share a glimpse into the fascinating world of the computational science and how it is revolutionizing our understanding of the universe. So here is a picture of a magnet, and I think there will be a question on it, so I won't answer the question before.
Yeah, so we've got a poll that's
Yeah.
just gone up, and it's about the picture that you can see on the screen now. And it is, what physical phenomena is displayed on the picture on this slide? And then the second question is also, can you explain why the object is levitating? So yeah, please do answer that if you know. You might have seen this before potentially. So yeah, we'll leave maybe 30 seconds to get some answers in, because so far we've only had 7 responses, and we've got over 100 people in this call. So we'll just give that another 30 seconds or so. All right, we've got about a quarter of you have answered now. We'll try and get that up to maybe 50% before we carry on. So yeah. Yeah, if you're not sure, you can just submit the poll empty, just to show that you're not sure about the answer. All right, perfect. So we've just hit 50% of people. So I'm going to end that poll now, and we'll have a look at the answers, and we'll see what everyone has said. So yeah, pretty much everyone has got superconductivity for the first question. A few weren't sure. Some said magnets, which is yeah. I think that's right. And then we've got for the second question, can you explain why the object is levitating? One answer on here. The metal reached its critical temperature, after which it has a resistivity of 0 and produces strong magnetic fields. All right, passing over back to you, Maylee.
Okay, so for that person who answered that, very good. So yeah, the phenomena is superconductivity, and so this materials was cooled. Usually it's cooled by nitrogen, which is very cool, like minus 70 degrees around, and so it's cold, and below this superconductivity critical temperature, and below this temperature, in fact, we call it this effect the Meissner effect, meaning that the magnetic field of the superconductor will just expand, and that's why he's levitating. I mean, the material is levitating because it's expanding his magnetic field. So exactly. So, who I am. I did a bachelor in physics and my MPhil in condensed matter theory in France, and my PhD in France also at the CA on high pressure physics. I will describe a little bit more high pressure physics after that. And so the title of my PhD was Study of some properties of superhydroids at high pressure and high temperature. And basically my PhD were separated into 2 activities. I was doing half of my time computational calculations on using DFT, so I will explain this later, which is quantum mechanics calculations. And I also did experimental activities to synthesize at high pressure those superhydrides, which I also explain later. And here is an image of a diamond on jet cells, which is the tool that we use to reach those high pressure. And right now I'm a postdoc at Cambridge. So as I said, in the Department of Material Science and Metallurgy. And I'm currently searching for superconductor at high temperature and ambient pressure. And so I'm doing only, most of my time now is doing computational calculations. So this is my group I'm working with, sorry. So my PI, the Professor Chris Picard, the group is the material theory group, and we can see that I'm the only girl in the group. And so these my four other teammates, there is one PhD student here, Kieran Bozier, and three postdocs. And I did little images near Dr. Lewis Conway and Dr. Pascal Salzbrenner to show you how attractive it is right now to do some computational calculations during your PhD or after that, because some company will really look into those skills. For example, Dr. Pascal Salzbrenner is currently working in a big company which is called ANSYS, doing software, and Louis Conway will soon leave us to go to work in Google DeepMind. So, what is computational science? So basically, it's the use of computers to solve very complex problems, whether in science or engineering. And it can combine physics, mathematics, and the computer science itself. So to model or predict some systems and how system will behave. So computational science is the key to tackling some of the great challenges right now we are seeing right now in humanity today. And for example, there are some examples. If you want to create better batteries for example, electric vehicles, or if you want to design new materials, for example, here, superconductors, and or in medicine to design new drugs or for disease, etc. So it had a very large panel of applications. Here's an image of the computational scientist. His role is so to apply the high performance computing in different ways to advance the state of the art in their respective applied disciplines, so physics, chemistry, mathematics, engineering, etc. And here you can see a pyramidal of all the disciplinary that touches the computational science. And here I am between chemistry and physics.
Yeah,
So,
so maybe before we carry on, actually, while we're thinking about computational science, I'm really curious to hear from you. So I've just got a quick poll, which is, have you ever heard of computational science before this seminar? So yeah, just shoot an answer in the poll. It's really, really quick. Just yes or no. Have you heard of it before? Because I'm quite curious to find out. Um, all right, so we had almost 80% of you answer already, which is great. And it's quite a split, actually, quite an even split. So we've got 62% of you have heard of computational science, and just under 40% have never heard of it. So that's much more even than I expected. So yeah, I'll end that poll now.
okay.
And then yes, I believe we've got another poll actually quite soon.
Yeah, okay. Don't, yeah, you can interrupt me anytime. So let's talk about now DFT. So basically what I've done during my PhD is what I'm doing right now. So DFT means density functional theory. And so what is it? I will not go deeply into it because it's a bit complicated, but just roughly so that you have a general idea of what it is. So one of the most exciting, I think personally, area of computational science is quantum mechanics. And so a method that was developed, a theory that was developed to study all these quantum mechanics tools is the density functional theory. So it's what is it? It's a powerful method that is used both in physics and chemistry to calculate the properties of materials at the atomic level. So basically, the quantum mechanics are rules by the equation that are called the Schrödinger equations here. It's a bit complicated. And the Schrödinger equation cannot be solved with many electrons. It can be solved analytically with only one electron, but when there are more than one electron, it's impossible. So that's how mathematicians and physicians developed the DFT, and it's a method which you have an equivalent system where you took all the electrons that you have and you say, okay, these electrons won't interact together. And so instead of tracking each electron individually, the DFT will focuses on the overall of the electron density. So what is the electronic density? It's the probability to find an electron in a certain space. And so this equivalent method system is basically to simplify the complex calculation. So you start with an impossible Schrödinger equation that you can't solve with the real system, and you have an equivalent system that you modified, and you have those equations from this modified system, but it's still equivalent, that you can resolve those equations. That's DFT. However, the DFT is an exact theory. So basically, the DFT is exactly the same as resolving the DFT calculation is exactly as if you were resolving the Schrödinger equation. But in reality, practically, when you want really to compute, since you don't know one part of the equation, which is here in red, the exchange correlation, this is this moment where we use approximation. And so that's why the DFT method is exact, but when we compute it, so practically, it's an approximation due to the approximation of the energy, exchange correlation energy. Not sure if it's clear, but so
Yeah,
basically
I think, sorry, really, really quickly, someone has asked just to clarify what is the exchange correlation?
it's the exchange correlation is part of the developed equation here. It's an energy basically that you need to add since you have an equivalent system where the electrons do not interact between each other, and in the real system they are. This exchange correlation emphasizes this to recreate the interaction between the electrons. And we can't compute it. We don't know the value of it. And that's why we have to approximate it. And that's why the application of DFT is not exact anymore, even if the development of the theory is exact. And so the aim of DFT is to predict how the atoms will interact between each other, and it will help scientists to design and discover new materials or study their properties, like for superconductivity or for creating new batteries or new medicines, etc. And so now I'll focus more on the field where I am, so the high pressure physics. So here is a basic picture how to understand the high pressure. So here on the left, you have when you are walking, a person who is wearing a sneakers. So there is the whole surface touching the floor is quite big. And on the other hand, on the left, you have an image of what could be high pressure, like women wearing some heels. The surface that touches the floor is even less here in the heels. And because the surface is way smaller with the same weight applied on this little surface, you have a very high pressure on this little surface applied on the floor
So yeah,
compared to the right on the
we've also
sneakers.
got a poll for this actually. So I'll just launch it now. So it's quite a quick one again. So two questions. First one is, have you heard of high pressure physics before? And then also, quickly, if you have heard of it before, what does it mean to you? And can you give any examples of high pressure? So yeah, I'll leave that up for another maybe 30 seconds. So far, we've had about a quarter of you respond, and 80% of you have said that you haven't heard of high pressure physics before. So yeah, I'll leave it up for another maybe 10 seconds or so. It looks like, yeah, maybe now it's more like 25% have heard of it, 75% haven't. So yeah, I'll end the poll there since we've had 3/4 of you respond, and I'll have a really quick look at examples of high pressure that you've given. So, oh, that's not coming up, unfortunately. So I'll let Maylee continue, and then I'll hopefully come back to this. Sorry about that.
Okay, thank you. So the high pressure physics is the study of how the materials will behave when they are squeezed under extremely high pressure. And what I mean by high pressure, extremely high pressure, is, as an example here, the center of the Earth. Like right now, there is a pressure that we feel. It's called 1 atmosphere, and in the center of the Earth, it's 3.6 million atmosphere. So imagine it's the pressure that we feel right now, but 3.6 million this pressure. And the unit that we use in high pressure is gigapascal. So 3.6 million atmosphere equals 360 gigapascal. So these are an example of extremely high pressure. And actually, in the lab, we can reach those very, very high pressures. So like deep inside our planets, like I said, or powerful explosion. And how can we reach those very, very high pressures? So we first need to have a material that is extremely hard. So can you guess? The diamond. The diamond is the most hard material that we have on Earth. So basically, the diamond is produced in high pressure. You start from carbon, for example, the graphite that you can find in your pencil, and you squeeze it at very, very high pressure, and then you get the diamonds. And the diamond is a metastable phase, meaning that it's created at very high pressure. But when you release it at ambient pressure, I mean, you can see diamonds in everyday life. So it means that the phase is metastable. And so we use those diamonds in the tool, and we squeeze 2 diamonds against each other with the sample in the middle. And that's how we can really reach extremely high pressure around the sample, squeezed between 2 diamonds. So now I will talk about some examples, how high pressure physics and computational calculation are used. So this picture, we talked about it. It's a superconductor in his below his temperature of critical temperature of superconductivity. That's why it's levitating. And so right now there's a very run to find a new superconductor that will work in ambient conditions, meaning that with a high TC. By high TC, I mean around room temperature, because normally TC is a phenomena that appears at very low temperature and at ambient conditions. And you can see with the years, we found more and more high TC superconductors, and the new class of materials that have the record of high TC are the superhydrides, in orange here on the top of the graph. And so what are superhydrides? So it's a new class of materials that were synthesized at high pressures. So this new class of materials are only found at very high pressures, like above 1 100 gigapascal. So it's 1 million atmosphere. And the superhydrides are basically a metal. Here you have like the lanthanum in blue with a lot of hydrogen. Here you have like 10 hydrogen per one atom of lanthanum. And what is funny about it is like the hydrogen will do some lattice between them. And here you can see there's some cage of hydrogen that will encircles each atom of lanthanum. And I did a computational calculations on this compound, LiH10. So at very high pressures, 190 gigapascal, and high temperatures around 2000 Kelvin, degrees Celsius. And so by doing this calculation, I follow, in fact, each atoms. So in white, you have the hydrogen, and in blue, you have the lanthanum. And what you can see is that the lanthanum will just vibrate. So they don't really move. They just vibrate around their position. So it's like a solid. And the hydrogen, you can see, they have trajectories, like they really move around the cell. So this is the in black here you have the cell, the box of the simulation. And so yeah, in red, green, and yellow, you have the real trajectories of hydrogen. And in fact, the fact that this compound is both a solid with the lanthanum sublattice and a liquid with this hydrogen that moves around, like it's completely diffuse. It's a new property that we have found in this class of materials, which is called superionicity. So superionicity, you have an element that acts both like a solid and both like a liquid. And the second example is during my PhD, as I told you earlier, I also made an experimental study to find a new superhydride recoverable at ambient pressure. And we managed to do so. And so I will conclude with how fantastic computational science is. We can here, like an example, design new materials for renewable energies, and a very hot topic right now is the quantum science, the quantum calculation. And here's an example of a quantum computer that works at very, very low temperatures because they need to be in their superconductor states. So if we manage to find a superconductor that works at ambient pressure and ambient temperature, it will be very, very interesting for this field, quantum calculations. So thank you, and I will be very happy to answer all your questions.
All right, thank you so much for the presentation. So I've had a look at some of the questions, and I'm just going right to the beginning. And someone has asked, is computational science a degree that you can do at university, or is it something that you specialize in later on?
I don't really know here. I'm not from Cambridge, but I guess you can have a degree. I mean, there is the Department of Computational Science, so you maybe have a bachelor or MPhil. I don't really know. I mean, I'm doing computational science, but I don't have any degree. I'm a physicist, so I have a bachelor and MPhil in physics, but I learn computational the DFT during my PhD. So. I mean, so if the question is, can we do computational science even if we don't have a computational science degree? The response is yes.
Okay, yeah, that's perfect. Thank you. And then somebody else has asked, what skills do you need to do computational science?
What skills?
Mm.
I mean, I guess every skills that you need when you are learning something new. I mean, you need to know to use a computer because since you will basically use it But I mean, you don't have to be a nerd or a geek to do computational science. I'm neither a geek or a nerd. So for me, if you are interested in this field, in the subject, everyone can do it. Like really, it's very accessible.
Mm. I think the one thing that I'd be quite interested in is what does it look like? What is, for example, one of the animations that you had on screen, somebody asked, how do you make that? So what are the sort of things that you do day to day in your sort of job?
Okay. So I'm sharing the window. Oh no, I will show my screen. Okay. So I will share my screen and show you, for example. So you can see my screen.
Yes, yes, we can.
Okay. So yeah, usually here is a terminal with some data.
Mm.
I have yeah up like this. I have some data here, and basically yeah, I mean, I'm using Unix command, and for example here, so I have some data here of structures that we managed to calculate. And now, for example, I'm using Vesta, which is a tool to open and see and visualize the structure. So up, and now I'm seeing a new structure of a that I need to study. So let's see, what is it like? Poedral, like it has a very strange face. Like you can see the cages. So in white, you have the hydrogen. The cages of hydrogen are around another atom. And yeah, basically this is what I'm doing. I'm generating some structures and then I'm analyzing it and then try to calculate the TC if it's an interesting, if the TC is high and interesting. Like yeah, you have many structures here. And for the coding, what I can show you. Yeah, for example, what can I have like here? Search. Yeah, for example, okay, I will show you. So this is an input file. So this is what look like. So this is an input file. You say, okay, I have lithium, bore, and hydrogen atoms, some parameters, and then I will launch my calculation. And as a result, I have many structures, and I can show you if it works. The results here. Oh, no, shit. Yes. So here is a result. Where is it? Here. So we discovered new structures in the ternary hydride. So it means ternary. There are 3 types of elements, and with that we it's called crystal prediction. So we'll try to with a code to discover many possibilities between lithium, hydrogen, and bore, saying like you can have a structure with 3 hydrogen, 1 bore, 4 hydrogen, 1 lithium, etc. And so we'll map all the possibilities, and we'll map it here on the only the stable one. Only the stable one are mapped here. But this was just an example of what I'm doing every day.
Yeah, I think that's really interesting. And what I was going to ask to follow up on that is just to check my understanding. And the way that I'm understanding is that you're using sort of computers and models to check what's possible before you sort of try to put it into practice and you actually try to create these things.
Yeah, exactly. The main asset and advantage of the those computational calculation and for the DFT calculation is we can't try to discover right now new superconductors by just doing experimentally all the possibilities, because all the possibilities will take too much time, like forever.
Mm.
And even with the calculation, it takes a lot of time. So that's why in my group, they develop some tools with machine learning to really accelerate the search on new materials, because the periodic table is quite big. And so, yeah, the main advantage of the computational is first, you discover a new material, you calculate all the properties of it, and if it's interesting, then we can try to synthesize it. It's better this way. Sometimes you can find it by chance. But this is what I did during my PhD. By chance, we found a new superhydride experimentally, but the most efficient way will be to first start the search with calculations, then you find it, an interesting one, and then you can try to synthesize it.
Absolutely. Yeah, thank you so much for that. I think that really helped add to your whole presentation. And just quickly, one sort of abbreviation that you've used a few times is TC. Would you mind defining that for us?
Yes, so the TC is the critical temperature of superconductivity. So what it means is you have your compound, and when we say it's superconductor, what we means is that below this TC, so this critical temperature, it becomes superconductor. So above the TC, it's like a regular, it's normal in its normal states, and below the TC, it's superconductor. So it has, and as being a superconductor, it has many properties with the resistivity that goes to zero, the expansion of the magnetic field, the Meissner effect. There is the Josephson effect, etc. There are many also properties of superconductors.
Perfect, thank you. So I'll get back to a few more questions. So one of the earlier questions we had again was, what does superhydride mean?
So I will share my screen again. So superhydride means play. So superhydride is what we call a new class of metals that is a metal with a lot of hydrogen. And why it's super? Because there's a lot of hydrogen. Basically, the ratio metal to hydrogen is at least 4. So for example, in H10, we have a ratio of lanthanum and hydrogen that is 10. There is 10 hydrogen for 1 lanthanum. Basically, the superhydride are always synthesized at very high pressures. And why it's called hydrides? It's because in chemistry, if you know, when an element is electrophile, so likes the electron, will take a bit the electron of the other element that is near him, and it will have more electrons than normal. So it's become a hydride for the hydrogen. So the hydrogen has normally only 1 electron, and the electronegativity of hydrogen is more important than lanthanum. So what it means, when you have lanthanum and hydrogen together, the hydrogen will take a bit of electrons of lanthanum to him. So hydrogen will get a bit more than 1 electron. It will be 1 and 1.1, for example. It's not that, but let's say that. And so it will become, hydrogen will have a negative charge. So it will become a hydride. So yeah, superhydrides. And there are many examples of superhydrides, like there are yttrium and yttrium H6, etc.
Perfect, thank you. So we've had quite a few questions about what you mentioned quite briefly, which is how you can use machine learning with sort of computational science. So someone has asked, you mentioned that one of your co-workers is going to Google DeepMind. So what's the link between computational science and machine learning?
Okay, so in our group, so what Chris developed is a method. So first he developed a method to search new materials. And so how do you search materials? You explore this configurational space. So the configurational space, imagine in your head, is like all the possibilities of configurations for a materials. For example, let's say you mix hydrogen and lanthanum. There are many possibilities, and all these possibilities form a surface which is called the configurational space. And on this surface, there are some saddle points, so like holes like this. And a hole means a minima. And so a minima is a stable structure. And so how to get new materials is like you have to explore the whole surface, but it's very difficult and very costly, I mean, in computational time. And so he developed another method, which includes machine learning potential to accelerate the exploration of the surface. So basically, normally what you should do is when you explore the configuration space is each time you go to a point, you will do a DFT calculation. So we do a DFT calculation, which is very costly because you are taking into account all the electrons, etc., to really take into account all the quantum mechanics. And so each calculation is very costly. And with his method, we use machine learning potential. So for each point, we do not do a DFT calculation. We just use the machine learning potential to relax the structure. And so it's a way to really accelerate the exploration. And this is one use of the machine learning in computational science here in DFT, in structural prediction, structure prediction.
Perfect, thank you. And then yeah, there are a few questions about DFT and specifically what the DFT calculations tell you and what they're sort of specifically used for.
So the DFT calculations really, because you are studying the materials with the quantum mechanics equation at the atomic level, you are really taking into account the quantum mechanics of the like for an example, you can predict how the electrons in the atoms will interact together or move together without any guess. This is the power of DFT. I don't know if you can imagine. You just, in your input, you just say, okay, I have iron and hydrogen. And that's it. This is only what the information that you're saying. So iron has this atomic mass, hydrogen has this atomic mass, and only with all this information, by resolving the quantum mechanics equation within the DFT formula, you can have and calculate all the properties of the compound without any first guess or experimental information. This is what we say that DFT calculation are first principle calculation or ab initio. So it means that there's no experimental or first guess before. It's really based on quantum mechanics and on the elements that you are putting into the calculation.
Brilliant, yeah. Thank you for that answer. And then we've got quite a specific question that I thought was quite interesting. So on one of your slides, you showed us a diamond anvil, which I've never seen before, and I think it looked quite cool. And someone has asked, how big does the diamond anvil have to be when you're using it in experiments?
Yeah, so here is an example. So you have the image of the diamond universals, and just above this, you have exactly what it resembles a diamond universal. So you have a euro. Yeah, sorry, we're in France, but it's a €1 piece, so it's like that big. And in fact, the diamond universals hold into my hands. So the two left part just go one into other. So you can see the little diamond in the middle. So like this, and then we put it on the part on the right, and we close it, and the little capillary, so it's the cord, we will put the gas into it, and well, in fact, it's the gas that will just push one part against the other, and each diamond is fixed to one part. So by pushing one part to another, you will push the diamonds one to another, and it really holds into my hand. So it's really
Mm,
not big. I mean, the diamonds that we use are very small. It's like that big. Maybe it's like 0.2 to 4 carat. So it's
mm,
not big diamonds, and the diamond we use are synthetic. So because we want the diamonds to be as pure as possible, chemically pure, I mean. And so the only possibility to reach that purity of diamonds, like almost 100%, it's like 99.999%, is to use synthetic diamonds.
mm. Brilliant. That's really cool. Thank you for explaining that. Um, so we've had a few different questions talking about. So obviously you showed us on screen what you do sort of day to day, and some people have asked, do you do much programming in your day to day? And if so, what programming languages would you use?
Okay, so I won't be a perfect example for this because since I had a PhD that was half computational and half experimental, I'm not into really coding, but my colleagues are coding, and so all the tools that were developed by Chris, my PI, were developed in Fortran. And my colleague, basically, they were developed in Python, and the only code I'm doing is a bit of Bash and and Unix commands to process the data and automatize some routines, but that's it. And my colleague, yeah, they will develop more in Python or do some Bash routines.
Mm, perfect, thank you. So let's have a look. Are there any more questions? Um, so yeah, this is quite a good one. So you talked a lot about sort of discovering new materials and in particular superconductors.
Mm.
And someone has asked, what is the significance of discovering these new materials? What can they be used for?
The superconductor or the
Uh,
just new materials in general?
I think just in general, yeah.
It depends on the property of the new materials, I guess. Um, for example, so I worked a bit on hydrogen storage also. So right now it's a very hot topic also for renewable energy, because hydrogen storage is a way to store energy, but greener way. And so there are many researchers that are trying to find and design solid materials that will absorb hydrogen, a lot of hydrogen. It's hydrogen storage. So what we want is materials that really absorb many hydrogen, that will keep hydrogen a long time, and then can release hydrogen very easily. And it's very difficult to design all that kind of materials. And right now, we don't have these perfect materials for hydrogen storage because most of the time, so the materials will absorb hydrogen, but not too much. Then we'll have to heat sometimes a lot so that it release hydrogen, and sometimes the material itself is can be toxic or isn't it's rare, etc. So yeah, for example, the hydrogen storage, there is real research to design the perfect hydrogen material to absorb and release hydrogen very easily and in a green way.
Mm, brilliant, thank you. And then if we were specifically to talk about superconductors, um, do you have any examples of what they could be used for?
Yeah, for example, so superconductors, when they are below their TC, there is a zero resistivity. So what it means is there are no loss of energy when the electrons are circulating. So it can be used for transmitting application, like in all our electric wires. there will be no loss of energy. So it will be a gain for efficiency and a gain of money also. For example, the MRI in hospitals, how they work is with a superconductor magnet, and those magnet has to be cooled at very low temperature because the ATC are very low, and cooling those magnets cost a lot of money because they are cooled with helium-3. Helium-3 is a rare case, and it's very expensive. And if we have a superconductor magnet that won't work at ambient conditions, it means that we don't have to cool all these magnet for the MRI, and the MRI will work very easily. And yeah, it will be also very efficient for hospitals because it could also a lot of money. And so it will be possible to have more MRI available in hospitals. And yeah, another example is like, you maybe know the maglev. It's the train that levitates in Japan. If we were to find a superconductor that works in ambient condition, we could have like a maglev train like very easily also. So there are many applications.
Absolutely, yeah. Thank you for that. So we've got a question about again the experiments that you spoke about. So someone asks, do you only use diamonds in high pressure experiments, or do you use any other hard materials as well?
A very good question. So as for me, I always use diamonds because, so when we say high pressure, it depends on high pressure. Like when we want to reach very high pressure, we always use only diamonds. But when you want to reach like lower pressure, let's say up to 10 gigapascal or maybe 20 gigapascal, we don't we can do not use we can't sorry, we can not use sorry, diamonds. There are another press that is called Edinburgh Paris press, which is very big this time, and it's not diamond, it's a very hard metal anvil, so very big. And the advantage of this is that because it's very big, the size of the sample can be bigger. And this is good because when you want to synthesize a bigger amount of sample and that the pressure needed is not very high, it's possible. Because here, like you can see, the diamond is very small. And the thing I didn't say is the diamond is very small, and the head of the diamond, so you have the two diamonds that will be like this and the sample in the middle. And the thing is, the head of the diamond is the surface here of the diamond, and it's very small. This is the collet, and sorry, this is the collet, and this is the base of the diamond. So the collet of the diamond is very small because, as we say for the heels, it's the same principle. We want to push the diamonds together, and so with a big surface here and a little surface here, will transform a bigger pressure in the middle. So because the collet is very small, the hole where the sample is also very small. Like here, the size of the hole is like 30 micrometers. So the sample here is like maybe 5 to 10 maximum micrometers. So the sample that we will synthesize is very small. And sometimes it can be difficult if you want to characterize the sample because there are some methods in experiments that we can't use on very small sample. So yeah, doing experiments with high pressure using the diamond cells can be restricting with the characterizing method. And so yes, we can also use not diamonds but moissonite. It's it's like a diamond. It's transparent, etc., like this, and it's less harder than diamonds, and you can use it for also experiment, and it looks like a diamond. So we can just replace the diamond over cells by moissanite over cells, but I've never used it because they're not harder enough for my experiments. But it's possible also.
Right, thank you. So we are sort of very quickly running out of time, unfortunately. So I'll just do the last few questions now. So for the first one, someone has asked, do you think it's easier to have a background in the science, so for example, a physics degree, and then move into computational science, or do you think it's better to have a computer science degree and then move into computational science?
I would say it's preferable to have a physics background. All my colleagues, all my team, are from physics, and they're coding and very well. I mean, you will learn the computational with working. If you prefer starting with computational science, you can do, but I feel that you will maybe miss something because physics it's a bit difficult. So yeah, I would advise to start first with physics, but I mean it's possible in both ways. So I mean, yeah,
Yeah, absolutely.
everything's
No,
possible. So, but
definitely. And I
yeah,
mean,
I would advise more to. I mean, depending on what you want to do. I mean, if you really want to do computational science and do really like machine learning, artificial science, maybe it's worth starting with computational science. But if you really want to work in research and in physics and do like the things I'm doing, for example, it's better to have started with physics.
brilliant. All right. Thank you. And then, yeah, so what we'll do is we'll say this is the last question because unfortunately we are running out of time. But someone has asked, how else is computational science used, for example, in areas like climate modeling, drug design, or material science?
How it is used?
How else is it used other than what we've spoken about in the seminar?
How often it is used? I'm sorry, I didn't really.
Oh, how else? So like other ways that it's used.
Okay. Uh, um, okay. Exactly. For example, to design new drugs, it's exactly the same. Just like me, I'm mixing elements, but for the drug designs, it will be like molecules or proteins, etc. It's basically the same idea. You will just design new materials by mixing and discovering new materials, but not with just elements, with molecules. But it's the same way. It's just you will work on bigger systems. So sometimes it could be the calculation might be a bit longer, but this is exactly the the same way of doing. Like I could do it if I want, but I'm not interested. I mean, my work is not interesting on those molecules. Proteins, etc. But it's you use the same models and the same methods, kind of.
Absolutely. Yeah, no, that makes sense. So would I be right in saying that there's a sort of equivalent equation that people designing drugs would be using to
Yeah,
DFT, but that's just specific to their area?
yeah, roughly, yeah. Because if you work on with molecules or bigger like proteins, etc., because it's bigger, you'll have to take into account more interactions like van der Waals, etc. So you will have some modified models, but yeah, roughly it will be the same.
Brilliant. All right. Thank you so much. That was really, really interesting and definitely something quite different for the series. So I hope everyone that has joined has enjoyed that. And then yeah, please do join us next week for the last seminar of the series. Yeah, so thank you so much,
Thank you.
Nili. And I'll be ending the call now. All right. Goodbye, everyone.
Goodbye. Thank you.